and it's a pleasure to have Tomohiro Fujita. So Tomo is a collaborator of ours, and he got his PhD at Kavli IPMU. Tomo, if I say something wrong, please correct me.
Okay.
After that, he was a postdoc at Stanford University, and then YITP, Kyoto, and as well as University of Geneva. And right now, he's at Tokyo University. So I leave you with Tomo, who's going to tell us about hunting axion dark matter with new techniques.
Thank you very much, Emma. And thank you very much for giving me this opportunity to visit Sydney for the first time and give a talk. So today I'd like to talk about the new way to detect or search for axion-like dark matter. So this talk is based on 3 PLL paper published with these 2 years with my collaborator mainly in Tokyo. Some of them are in Kyoto in Japan. Okay, let's get started. So this is talk about dark matter, axion-like dark matter, but I also talk about these things: protoplanetary disks, gravitational wave interferometer, and optical link cavities. So apparently they have nothing to do with dark matter or like cosmology, but my main message of this talk is, so these things, protoplanetary disks, gravitational wave interferometer, and optical link cavity provide a new and one of the best method to search for axion-like dark matter. So basically I will introduce you a couple of new ways to search for dark matter. I'm afraid I don't have enough time to tell you all of 3 things, but I think I have time to tell you the first 2. Okay, let me start with introduction. So the question is, so what dark matter is? Who is dark matter? We don't know. We are all sure that dark matter exists in this universe, but we don't know what it is. And there are a bunch of proposals of the nature of dark matter. So from scalar modified gravity, primordial black holes, others, and WIMPs and neutrinos. And among them today, so we forecast on scalar type dark matter, so which is here in this plot. And I won't tell you the detail of how this kind of scalar dark matter is produced in the early universe or evolution of the history of the universe, in the history of the universe of this kind of dark matter. But the point is, it is known that, so if you solve the equation motion for scalar type dark matter, you get this solution. So this is a solution of equation motion. So phi, this dark matter, is given by damping oscillation. So its amplitude is damping due to cosmic expansion. This A stands for scale factor, which represents the size of the universe. And on top of that, it has a cosine factor, and M is the mass of this scale dark matter. So basically, this field oscillates around its mass potential. And in that case, with this solution, it is known that it can be a dark matter. It satisfies the property of dark matter. Okay, so this oscillatory feature is very important in this talk. But once you assume that scalar field is dark matter, this is a natural consequence. So the scalar field has to oscillate around its mass potential to be a dark matter. Okay. Then, and on top of saying just scalar dark matter, I also say axion-like dark matter or axion. So what do I mean by saying axion? So these 3 properties are properties of axion. So first of all, axion-like dark matter can be very, very light. So as light as 10 to the minus 22. So listen to some people say Lyman alpha observation puts some lower bound, slightly larger than 10 to the minus 22. But anyway, so roughly what I would estimate, it's around 10 to the minus 20 or 23 electron volt. It's very, very light compared to other standard model particles. And second, axion is shear scalar field, so it breaks parity. So once this axion-like dark matter is involved, the physics of left-handed mode and right-handed mode can be different, very different. That's a very interesting feature. And third, So axion, or axion-like particle, may be coupled to gauge field. And here we assume that so axion is actually coupled to U1 gauge field, which is photon in standard model. So we assume axion is coupled to photon. So it can be a huge advantage to search for this kind of dark matter because we can have a very advanced technology to manipulate photons, and we can use them to search for dark matter if dark matter is coupled to photon. Right? These are three important characteristics of axion-like dark matter. Okay, and let's discuss more in detail about axion-photon coupling. So that coupling in Lagrangian is given so later in this way. So this is so-called Chern-Simons coupling. So G is just a coupling constant. So in the unit of GV inverse, so it's a constant, and phi stands for axion, and the FF tilde as a F is field strength of U1 gauge field photon, and F tilde is its dual. So with this Lagrangian, this is the interaction Lagrangian plus normal kinetic term, we can write down the equation motion for both photon and axion. Left-hand side are normal ones. So in the case of photon, it's a wave equation, and in the case of axion, which has a mass, satisfies the Klein-Gordon equation, as you know. But due to this additional interaction term, we get the right-hand side term. So these are coupling term between photon and axion. So they are coupled equation. Right? And conventionally, okay, this is a consequence or equation motion with axion-photon coupling. And conventionally, people consider about magnetic field, because as we learn in classical electromagnetism, so you see, so this is a rotation of vector potential. So A is a vector potential, okay, normal photon. So rotation of vector potential is nothing but magnetic field. So this coupling term, new terms in the right-hand side, is proportional to magnetic field. So conventionally, people consider to apply static magnetic field in the laboratory to use this coupling term. And if you apply this constant magnetic field, so we can replace that the rotation of A with this B naught. So this is what you apply by yourself. So B naught, and this right-hand side terms are proportional to B naught. So it means, for instance, axion wave goes into in the region with magnetic field, static magnetic field. So that means so we have this magnetic field term and the phi dot, because if axion is a particle and it can be represented as a wave, plane wave, for example. So in that case, we have a non-zero right-hand side term, so non-zero source term, which produces photon. So photon is produced, and the opposite thing can happen as well. So this is known as the axion-photon conversion process, or Polimarkov effect, sometimes called. So this interaction, this phenomena, axion-photon conversion, is used in several experiments. For example, one of the most famous one is this CAST experiment conducted at CERN in Switzerland. So the idea is kind of simple. So suppose that some axion is produced inside the sun, our sun, and some of them are flying towards us, and we waiting for such a solar axion by applying magnetic field inside this facility, CAST experiment. And these axions, solar axions, going into this facility is supposed to convert it into photon, right? Because we have magnetic field and axion. So converted photon is detected by this X-ray detector. So through this way, we can detect the solar axion. So it's a simple idea, right? So experiment with axion-photon conversion. So this is the current status of axion-photon coupling search. So x-axis is axion mass in the unit of electron volt. So here is 1 electron volt, and here is 10 to the minus 20 electron volt. So kind of lower bound for dark matter axion. And the y-axis is axion-photon coupling constant G in the unit of GV inverse. And this blue shaded region was excluded by CAST experiment, which I just explained. Right. So benchmark value for coupling constant is around 10 to the minus 10 GeV. And the semi-astrophysical observation put slightly more stringent constraint on coupling constant. And this yellow band is a case for QCD axion. So these two are most famous models for QCD axion. And you can see here, okay, out of the QCD axion band, we have a huge empty space to search for axion-like particle. So this is the situation. So this is the possible region for axion-like particle dark matter. And in this talk, we aim to search for axion here in this region. Okay, so what's the idea? So far people considered to use, exploit these right-hand side term, source term, by applying magnetic field. So anything other than magnetic field can be used. So our idea is, okay, let's assume this axion is actually dark matter. So 100% of dark matter for simplicity. So then, so as I explained in the first slide, so once you assume this axion phi is dark matter, it should oscillate around its potential, and we know we know its behavior. So here I ignored cosmic expansion, so because like scale is much shorter than Hubble time scale. Anyway, so since we know this phi of function t is given by this this equation, so oscillates around its mass potential, so cosine mt. So we can plug this behavior into right-hand side of the equation motion for photon. Then, so this equation motion photon becomes just a linear equation in terms of photon. So we can write down dispersion relation of photon using left and right circular polarization basis. So dispersion relation can be written in this simple way. So omega square equals to k square. That's the normal part. But on top of that, so this we got this additional term. So g is coupling constant. So in the limit g goes to 0, so we produce normal one. So omega square equals to k square. But if g is non-zero and the axial amplitude is non-zero, we have this additional term. And it's interesting to see this new term has a flipped sign. You see, plus minus. This is a manifestation of parity violation of axion-like dark matter. Okay, so this dispersion relation implies that the speed of light actually changes depending on circular polarization of photon with a non-zero density of axion-like dark matter. Okay, this is the phenomena we want to use. We want to use to search for axion-like dark matter. So sometimes it's called axion birefringence. Okay, so that's the introduction. So do you have any questions so far? Is it okay? I guess. Can you hear me?
Yeah. We can hear you well.
Okay. Yeah.
Tom,
If
we'll
nobody
reserve the question to the end.
So no question. Okay.
Oh, Bruce has a question.
So sorry. Yes. Go ahead.
No, that was a thumbs up saying that it was okay, since you asked for a response.
Ah, okay. All right. Yeah, please interrupt me anytime if you have a question. Okay, let me keep on going. So let's think how to use this phenomenon of birefringence to detect axion-like dark matter. So birefringence. So again, birefringence means a dispersion relation is changed. Dispersion relation of photon is changed. Okay, let's consider the case that the photon, this guy, travels along with z-axis from time t to t plus capital T. Just it goes straight, lying along the z-axis because it's photon. And let's consider linear polarization photon. So in that case, polarization of photon can be written in this way. Here I assume the polarization is along with x-axis, and I suppress z-axis, of course, because photon has a transverse wave. So Z component is always 0, so I don't have to write it. And as we learn in classical electromagnetism, so this linear polarization can be always decomposed into circular polarization, left and right polarization. Okay, and that modified, so this birefringence modified dispersion relation means these two left-handed mode and right-handed mode gains the opposite sign phase during this travel. Right? So here I write down this polarization component after this travel. We have a common part, but the common factor. Well, on top of that, so left-handed mode, for example, if left-handed mode gain the positive phase, so right-handed component should gain the negative phase, right? And if you combine them, we get this expression, cosine and sine. So it means originally the linear polarization along with x-axis is rotated due to this phase, right? So it's a simple physics. And okay, let's calculate. And what was the delta omega? Delta omega is this additional term given by axion-photon coupling proportional to Z coupling constant. And since it's basically this part is given by time derivative, but we want to integrate over this effect. So we want to time integrate this time derivative. So it just depends on boundary condition. So this is a very interesting feature of birefringence. It doesn't depend on what's going on like between the emission point and observation point. It just depends on boundary. Exactly speaking, it just depends on the axion field value at the boundaries. So it's a very simple physics. And I have an animation to explain the situation. So without axion, so this is this yellow point represents the polarization of wave of photon, so traveling perpendicular to this screen. This is a normal linear polarization photon. But if you turn on the coupling between photon and axion, so it becomes like this. So photon polarization, linear polarization, gradually rotates in phase with oscillation of axion like dark matter. So this is about like consequence of axion birefringence. And if we go, so when axion goes to right, it rotates to the right. It's interesting. All right, and as a result, we expect to see some non-zero, like a rotation of the linear polarization plane as a result of this axion birefringence. Yes. Okay, let's estimate how large is it? How large it is? Okay, so this phi, so this angle, rotation of the linear polarization plane induced by axion-photon coupling. If you plug some number, here I plug lowest possible axion mass, 10 to the minus 23 electron volt, and highest possible axion-photon coupling, 10 to the minus 12 GeV inverse, and also plug so capital T, travel time of photon, 10 parsec scale. So I consider astronomical observation. So in that case, the order estimate tells you that the size of this rotation angle is 10 to the minus 2. So it's not tiny. So it seems like we can observe it. But here's the problem. So how can we observe this? In astronomical observation, it's hard. Normally, it's hard to know the initial polarization plane. So we can observe, if we observe the linear polarization photon, we can of course like measure its polarization angle, polarization plane at our observation point. But it's hard to see the initial polarization plane, and we need to know both to measure the rotation angle, right? So this is why we focus on this. We come up with the idea to use this protoplanetary disk. I wasn't familiar at all with this protoplanetary disk. I had just heard of it before working on this topic. But okay, now I tell you that protoplanetary disks is a flat and gaseous object surrounding young star, and planets like ours are supposed to form inside this disk. So basically, a disk is formed around the star, like a very young star, before the formation of planets. And as time goes by, these planets are formed inside this gas. Okay, and this is a real data. A bunch of different protoplanetary disks are observed. And PPD itself, they don't light, they don't shine by themselves, but they are bright simply by scattering the central star's light. It's just like planets. Right? So that means, so since we can observe them as a scatter light, it's polarized. And it's polarized perpendicular to scattering plane. So this is a simulation result of polarization plane. So this center point, so this is a PPD on axis or on face on type PPD. And these small red line shows the polarization plane of linear polarized photons coming towards us. So you can see the very beautiful concentric pattern as a result of this simple physics. Yeah. So this is a simulation result. What happened and what kind of linear polarization is produced at the position of PPD. And so these photons produced there or scattered there coming towards us. And during that process, during the travel from PPD to ours, so axion birefringence distort their axion birefringence is expected to distort this polarization pattern from this concentric pattern into this spiral pattern, right? Because at each point, the axion rotates a linear polarization plane of photons. Right? As a result, we expect this kind of spiral shape. So all we need to do is very simple, just measure this theta, this angle theta, and ask if it's a 90 degree or deviate from 90 degree. So this is a real data, real observation result of Subaru telescope. And our target was Area Aguirre, 160 parsec away from us, and not very far inside our galaxy. And result is, unfortunately, it's consistent with 90 degree. So result is 90.1 plus minus 0.2. So we didn't discover smoking gun of axion dark matter. But of course, we can put the upper bound as a result of this observation. So here, this is our result. So x-axis is mass of the axion-like dark matter. So here is 10 to minus 22. And the y-axis is a coupling constant between photon and axion in the unit of GeV inverse. And these are, this blue shaded region is cast, supernovae, other astronomical observation previously put, bound. And this black line is our new bound. So for certainly like sufficiently small mass of axion-like dark matter, our bound is the kind of best, most stringent one. And in particular, so many people discuss about this mass region, 10 to the minus 22, as a fuzzy dark matter, which has extra motivation. So if you focus on this mass bound, so our bound, like our constraint is the strongest, strongest constraint. So we got excited. Okay, is it clear so far? So,
Tomo, can I ask a question about this plot?
Yes.
Yes, so the part that is colored in blue and green and red, is that all excluded?
Yeah, yes.
Ah, okay.
These are previous works.
And that's all excluded, I see.
Yeah, well, they have been excluded
okay,
before us. And it was a kind of best. So our bound was the best, but shortly after our paper, so other people consider axion-like dark matter in the similar mass range, and they used a CMB observation. So here I don't explain the detail of this work, but it's great work. So their constraint is the first constraint from CMB on axion-like dark matter. Anyway, the point is this black solid line is this line or constraint, but so these people succeeded in putting a stronger constraint, which is this green shaded region. So it was already updated. So just a few months later. So it's very hot topic, and many people are working on this topic. But okay, this is our current situation. But we expect we can improve our constraint by using the fact that this was, as I explained, by using animation, this rotational polarization angle is in phase with axion oscillation. So as a result, we expect to. I made this animation right before this talk, and it's not very good. So please ignore the vertical motion. I just wanted to make a horizontal oscillatory movement, but I couldn't do that with my PowerPoint. Anyway, so we expect to see that this theta is oscillates in phase with axion oscillation around its potential. So that means if you observe one PPD, or like multiple PPD if you want, so if you observe a PPD for a longer time than this oscillation period of axion, we expect to see this periodic shift of the polarization. So we can use that in principle. There is no such observation. There is no long-term observation of PPD so far. But if we can do that, so this is a paper by other people, not myself, but they forecast the future axion dark matter search in this very ultralight mass range. And this blue line, this green line is a current bound by Planck. So this one, green shaded region, is here. I drew it by myself. And in the future CMB observation, so-called CMB stage 4, will reach, okay, according to those people, of course, they made some assumption, but according to them, so CMB S4 can reach this level, so a little bit more than 1 order of magnitude better than current Planck bound. But if you use long-term observation of PPD, protoplanetary disk, you can reach as far as this sensitivity, so more than 2 orders of magnitude better than current one. So PPD has the biggest potential, so we want to continue to seek using this PPD observation to search for axion-like dark matter. Okay, that's the story of the section 2, protoplanetary disks. So do you have any question about PPD? Is okay?
I ask quickly.
Yes.
How far away are the protoplanetary disks?
How far away are the PPDs? Okay, so this particular one is 160 parsec away, so it's one of the closest one. And sorry, I'm not expert on this topic, so I don't know how much population of PPD distributed around this range, but
is the PPD, and so us and the PPD are within a de Broglie wavelength for the axion field, for the axion masses that you're probing?
Say again, sorry.
So how
no,
de Broglie wavelength for the axion?
I think I get your question. So you asked, so ours and this PPD are within one patch of coherent oscillation of axion. Is that the question?
Yeah.
And the answer is no, but it doesn't matter. Yes, that's a very good question, and I made a mistake when I uploaded the first version of my archive paper. But yeah, the point is, so where is that? Yes, so this rotation angle doesn't care what's going on between the emission and observation. So it doesn't matter the distance, whether distance is larger than coherent patch or smaller inside a coherent patch. It doesn't change the result. It's a little bit counterintuitive, but I was convinced that this is true.
But would you get a larger angle if you were within a coherence length or a de Broglie wavelength, or does it just doesn't matter at all about what the, because that is going to be changing the value of the axion field at the initial scattering and the detection.
Sure, okay. So short answer is it doesn't matter, but if ours and our target is too close, so the time scale is shorter than its one oscillation. Yeah. So in that case, yeah, I think you have already understood, but before this, like a rotation angle reaches its maximum value, if you, way before that, if you observe it, so resultant rotation angle will be very small. But if the distance is larger than mass inverse scale, much larger than mass inverse scale, it doesn't matter at all.
Thanks.
Okay.
So maybe just let me ask one follow-up question.
Mm-hmm.
You say you need to observe these for a longer time period. What kind of time period do you consider here?
Okay, it depends on mass scale. So this again, this oscillatory field. Yeah, okay. Let me tell you just one. So this 10 to the minus 22 electron volt fuzzy dark matter mass range correspond to 1 year, almost exactly 1 year of period. So this oscillation time scale is 1 year in the case of fuzzy dark matter, and if mass is larger, time scale is shorter. And another frequently asked question is, how long does it take to take this one picture? And it's only 3 minutes. Just a 3 minutes of exposure time give you this
does that mean,
resolution.
So that means if you go to larger times by 4 or 5 orders of magnitude larger time, then the oscillation would be so fast that you don't see it.
Yes. That's also true. But in any case, so if this sensitivity, as you can see from this sensitivity curve, so for higher mass, this birefringence is not very sensitive.
Yeah, I see.
So yeah. Or the same thing can be seen in this plot. So you see these gray shaded regions are already excluded by other experiment, and so all these techniques which use birefringence, axion birefringence, is sensitive, more sensitive on smaller mass scale and less sensitive for larger mass scale. Okay, so let me move on to gravitational wave interferometer if there is no additional question. Okay, so a couple of years ago, we detected gravitational wave for the first time from a binary black hole, and now we have a bunch of gravitational wave interferometers to search for gravitational waves. And now the question of the second section, section 3 actually. So can we use these gravitational wave interferometers to search for axion-like dark matter? And yes, it turns out it's a very good. So gravitational wave interferometers are very ideal facility to search for axion-like dark matter by using axion birefringence, because it has a very long baseline. In the case of advanced library, it's long as 4 kilometers, and each photon reflects many times, typically 500 times. So 4 times 500. That is like a distance a photon typically travels inside this cavity. And so gravitational waves is of course designed to detect tiny signal. And finally, so this laser used in gravitational wave interferometer is a linear polarized laser. So now it's almost trivial how to search for axion-like dark matter by using gravitational wave interferometer again. So we expect to, this axion birefringence is supposed to produce this rotation angle of linear polarization photon. And this time we know the initial linear polarization plane because our laser produces this polarization plane. So it's pretty simple that we decompose by using a filter, just get rid of this original component, the component of the original polarization plane, and take out the other perpendicular component by using a filter, and ask, so if there is such a component. Yeah. If there is no axion axion-photon coupling, we expect no such a signal, and if there is axion birefringence, we expect this kind of signal. Okay. And the advantage of this proposal, this technique, is it can coexist with gravitational wave observation. So it doesn't disturb the gravitational observation, which is the main purpose of course, gravitational wave interferometer. By adding, in principle, just by adding one photodetector here or there, so before the cavity or cavity. So as you know, so gravitational wave interferometer has two arms. But just to search for axion like dark matter, we need just one arm. And by adding one photodetector here or there, just one is enough. So it's very cheap. So yeah, so additional instrument at the tail of this cavity or before the cavity enable this gravitational wave interferometer to search for axion like dark matter. Okay. And this is a sensitivity curve for one year long. So again, these are, they have been, so this is a cast excluded region. And as you see, like a sensitivity is not much better than existence exclusion plot, exclusion region compared to other experiment. But again, so it can be done very cheaply. Without paying a huge cost. And if you use futuristic gravitational wave interferometer, you can improve by a few orders of magnitude the sensitivity. Yes.
Tomo, just a quick question.
Sure.
This extra instrument that you can possibly add to ground-based interferometers, can you do that with space-based? Is it something that people are thinking of?
Yes. So this DISIGO is a space-based interferometer, this proposed one. And okay, and probably you consider about the LISA?
Yeah,
maybe?
That's what I have in mind, yes.
Yes, okay. That's a good question. So I don't remember well, but I think in the case of LISA, we cannot use this technique for some reason, which I don't remember.
Okay.
I
Good to
I don't remember why, but normally photons reflect many times inside a cavity. That's normally what's going on in the ground-based interferometer. But the LISA is different. But sorry, I don't remember the detail.
Oh, no worries. I'll keep it in mind. Thanks.
Okay, but that's a good question. Yeah, I think so, because if LISA is possible, for sure I would like draw such a line here. But, so since there is no LISA line, so that means we cannot do that.
In LISA, they emit a new photon through some kind of phase-locked loop.
Mm-hmm.
So it's not the reflectance of a single photon, if you like, that's going back and forth. They're actually having a laser that emits a new photon through some kind of phase-locked loop, and that might affect it.
Yeah, but if it's a new photon, it should have a rotation effect. But okay, I don't remember why. Okay, LISA, I think it's difficult to use LISA. Okay, so this part is.
最早在湖州区的这个芦苇，然后雨花区的这个叫啥呢？就是我们物理的这个一把手就打，那一共才几个区啊？
That was not me, Tomo.
Yeah, that sounds like Chinese. But anyway, and okay, this proposal is kind of simple, and I said it's supposed to be very cheap, so we should be able to do that in the near future. And actually, we have just applied for a big round in Japan, so we are seriously thinking to add this new ability to our gravitational wave interferometer Kagura in Japan. So this is a PI, principal investigator of this grant. So actually, he was my PhD advisor. So we're making some effort to make it happen, actually. So finally, so let me tell you the third way to search for axion like dark matter, optical link cavity. this is a little bit more complicated than others. Okay, so I'm sorry for this very busy plot, but this is a situation. So again, so the situation of many proposals. So again, figure as x-axis is axion mass and y-axis is the Cartan constant and unit of GeV impulse. And these solid lines pre-exist. So the previous work, they are real constraint lines, but these all dash lines are proposed experiment. There are many things. For example, this abracadabra striking line is proposed by MIT people. And in principle, they claim they can reach this sensitivity, but last year they achieved so far they achieved here. And this third proposal, our third proposal, that sensitivity curve is this dance. We call it dance, our third proposal. So our prototype dance Act 1 is supposed to achieve this sensitivity curve, red dashed line. And in the future, we want to make it 10 times bigger, 10 meter. It's still like a tabletop size. It's not big. And we can achieve, expect to achieve this very good sensitivity in the near future. So let me explain what's the third proposal. So this is the situation. And just let me remind you that this purple dashed line is the one of gravitational wave interferometer. So this is not so great because, so of course, gravitational wave interferometer are not designed to search for action like that matter. But this other proposal is just to propose to build up a new facility to search for action like that matter. That's why this is very good compared to gravitational wave interferometer. Also, it's very small, just 1 meter size. So come back to this birefringence. Let me remind you this modified dispersion relation. Okay, so speed of light changes depending on its circular polarization. So let's consider another way to use this phenomena, birefringence. So now dispersion relation is modified. That means if you fix the travel distance, number of oscillation changes depending on the polarization. So let's consider a light polarization photon. Light polarized photon, like a wave behave like this. So left polarized photon can be something like that. So oscillation frequency effectively changes. So our idea is, okay, let's put a mirror here such that the light polarization photon shows a resonance. In that case, since left-handed photon has a different phase velocity, it doesn't show resonance within the mirror. So that's our idea. So let's put it again. This product is simple. So optical length changes for left and right polarization. So resonance frequency changes. And this is a short review of normal Fabry-Perot resonator. So EI, okay, let's consider. So we make an incident wave from laser, and EI is an incident photon or electric field going to this cavity. And some of them get reflected, and some of them go into this cavity and get reflected many times. And some of them go out from to the right, and some of them eventually reflected to the left. And so of course, and this ET, so resultant photon or electric field can be calculated as a sum of the, okay, just first term is a case that the photon never reflected, and second term is just reflected twice, reflect here and go out. That's the second term, and you can continue this business. And the final result is this. And the result is, okay, let's skip the detailed calculation, but the result is, in this case, in this simple Fabry-Perot resonator, and let me set this, these two mirrors are same. So reflection rate, RF and RE are the same. In that case, at the resonance, all the photon, EI, equals to ET. So all the photons just go through this cavity. Okay, it depends on reflection rate, but in that case, so roughly speaking, cavity virtually vanishes at the resonance. It depends on the rate of RF and RE, but in the case RE equals to F. RF equals to RE, or the photon eventually goes to light. So that's a simple case. So please keep it in your mind and just look at this. So our proposal, this is a coordination, like a configuration of our proposal. It looks a bit complicated. But let me explain quickly. So let's first forget this part. Let me explain. So we use laser and use some facility. We can make it circular polarized photon. Okay, let's say a left-handed photon goes into this cavity. And the cavity is set up such that photon goes this way. So it is called the bow tie cavity, since this shape looks like a bow tie, tie. If you rotate 90 degrees. And please remember that every time photon gets reflected, its polarization, its circular polarization is flipped. So first photon, so originally photon is left-handed and gets reflected here, so it becomes right-handed. So I denote it by blue line. And it gets reflected here and becomes red, and red becomes blue, and it goes around inside this cavity. And I set detector A here, and some of the photon goes out from this cavity and go into this detector A. And please note that, so inside this cavity, so since this cavity configuration is stretched vertically, you see, so these blue lines are longer than red line, right? So inside the cavity, so photon is almost always right-handed, roughly speaking, right? And eventually we observe right-handed photon. So by using this detector, so by using monitoring from this detector, we can tune the frequency of our laser such that this almost right-handed photon shows a resonance. So this cavity is now like a, so we tune the frequency of this instant laser such that this cavity shows a resonance. So in that case, so detector doesn't see any photon because all the photon goes there. Okay, and now I uncover this part, and actually we have a fifth mirror, and this photon get reflected additionally and go back to the cavity. And the point is, since these photons go back to the cavity, get additional reflection here, so polarization is flipped. And this time, so photon goes to the other way around. And please, the point is, they are almost left-handed. So this time I show them as a dashed line. And in the case of dashed line, so red line are much longer than blue line. So and they are almost always left-handed photon inside the cavity, and they goes to monitor detector B. So detector B checks if the left-handed photon shows a resonance in this cavity or not. Okay, and if I'm sorry that it's a little bit complicated, but the point is, so this experiment is designed to see the difference between right-handed photon and left-handed photon. And since we have tuned the frequency such that the almost right-handed photon shows a resonance, so this detector B, which checks the resonance of left-handed photon, can tell you if there is a difference of phase velocity between two circular polarization. Okay, did I make myself understood? And, yeah. If you have a question, please ask me. It's a projected sensitivity. So this is due to this special design, we can achieve this very good sensitivity. Also, it's very small, just 1 meter size. And in the future, we can make it, we plan to make it 10 meter size. And okay, and we have already started building up this. Okay, so this blue line is a prototype, 1 meter size, and we have already started making it in the laboratory of Tokyo University. You can see this photo. So it's so this size is 50 centimeters. So like a travel distance of photon is a typical 1 meter size, right? And, so it's being constructed in Tokyo, and we got some grant. And we originally planned to have a result within a year, but now because of this coronavirus outbreak, I don't know, our like a future plan is very unclear. But so we hope to resume this experiment again soon. So that brings us to back to this figure. So due to this special design, so we can achieve these red dashed line and the purple magenta dashed line. So by this dance experiment. Okay, so it's almost 1 hour, and let me summarize my talk. So axion, like dark matter, so axion can have recoupling to gauge field, and in many cases we assume the axion is actually coupled to our photon U1 gauge field. So in that case, so axion has been constrained or axion has been searched by using this axion-photon convergence so far. That's a conventional technique to search for axion like dark matter or axion like particle or axion, QCD axion itself. The same coupling, this Chern-Simons type axion-photon coupling, causes another phenomenon called birefringence, axion birefringence, if axion is dark matter. So that's so please, this is I want to make it clear that we need additional assumption compared to axion-photon conversion. So here, axion birefringence takes place only with the non-zero density of axion, and that assumption is naturally satisfied if you assume axion is dark matter, because in the galaxy, inside our galaxy, there are a bunch of dark matter, right? So same coupling plus additional assumption of dark matter. So axion causes this birefringence. And so we made a yes.
Do you need for all the dark matter to be axions, or is there like a lower bound on the density for the condition to be satisfied? The condition is, in principle, it's like just a non-zero amplitude is okay. Mm-hmm. So it doesn't have to be 100% of dark matter. But of course, if the fraction of axion dark matter to the total dark matter is smaller, so the resultant birefringence gets weaker. Yeah. So all those couplings are gonna become weaker.
Yes.
Yeah.
Yes.
Okay.
Is not that required also to have either inhomogeneity in the field or the time dependence? Because otherwise it's just a topological term. It won't give you any.
Yes, yes. So in this case, so since we consider axion as a dark matter, it oscillates around the potential. So that time dependence is used.
Of course, yeah.
Yes. So yeah. So optical link cavity and the gravitational wave interferometer are sensitive to the axion like dark matter in this, roughly speaking, this mass region. So intermediate mass region. Still, it's very weak, but slightly larger than fuzzy dark matter. And the protoplanetary disk, the one I talked at the beginning, is sensitive to ultra-like axion dark matter or fuzzy dark matter, like the smallest mass region. And I think this axion birefringence, so I didn't tell you that at the beginning, but this axion birefringence, this phenomena itself has been known for a long time. Like I think it was first pointed out at the beginning of the 1990s, but people didn't consider to use this phenomena to search for dark matter axion. So there is a good chance to work out a new idea, like a new proposal, a new experiment to discover axion like dark matter. So I think it's a very exciting topic. So if you're interested, let's work on that together. Thank you very much.
Okay, thank you, Tomo. Now there are more questions for Tomo. I'll ask just one and then leave everyone else. will the LIGO people put the little device to do the measurement of the to search for the axion dark matter? Do you know?
Really?
So
say that again?
Should I ask again? Yeah. No, I'm just wondering, will the LIGO people will actually do the measurement? Do you know? Is there is
I don't think so.
Because you don't think they will be willing to add the little device to do these measurements?
I don't know, but I don't think they're seriously plan to do that at present because it's okay for a theorist, and I'm one of the theorists, so it's like it looks very easy to introduce a new one photo detector, but now I know it's very hard to convince them, experimenters, because they of course these gravitational wave interferometers are very finely tuned, such that achieve the best sensitivity to search for gravitational waves. So they are very worried about that introducing these new photo detector introduces or produces additional noise, and which reduce the sensitivity for gravitational waves. So we need R&D, research and development, very carefully to convince them and really introduce new photo detector to search for axion like dark matter. That's why we have applied for new grant and want to hire a new postdoc, just work on this R&D. So anyway, it's an experiment. It's very it's not very trivial. Just say introducing a new facility, a new photo detector is easy, but in reality it needs a lot of effort. Now I know that.
I see.
Tomo, just on that matter, can you remind us? I mean, the dedicated tabletop experiment that you were discussing is going to be intrinsically more sensitive because it's directly targeted at this, but it likewise will be much smaller. So can you remind us how the sensitivity of one compares with the other? There may be different regimes.
So, okay, so this is a bit busy and messy plot, but this purple dashed line is gravitational wave interferometer in the case of LIGO. And so this red dashed line is our third proposal, dance experiment, 1 meter size. So it's a 4 kilometer, so 4,000 meter. And this magenta dance, advanced dance, is a 10 meter size. So mass range is slightly different, but it's
so the 10 meter design would already outperform advanced LIGO.
And I can tell you why.
Everywhere below 10 to the minus 11.
Yes. Okay. Let me tell you why. So here let me explain what's happened. Okay, let me explain to you in the way that why the sensitivity of gravitational wave interferometer is so bad here. So low mass region. So the reason is kind of simple. Okay, here, and please remember that every time photon gets reflected, its polarization flips. So, and on the way, let's consider one photon, single photon inside the Fabry-Perot cavity in the gravitational wave interferometer. So on the way, one way from left to right, it rotates in the one way, clockwise, let's say clockwise. Well, once it gets reflected here, so this polarization is flips and start rotating opposite way. So first way, on one way it rotates this way, for example, and on the way back it rotates backwards or counterclockwise. So this effect is cancelled. In the limit that oscillation of axion, oscillation period of axion is much longer than time scale of this cavity, time scale or a length scale of this cavity. And okay, let me go back to that slide. So whether the polarization rotates clockwise or counterclockwise, depending on the axion field, whether this guy going left or going right, right? So while this guy goes left, so it rotates to the left, and while this guy, the axion rotates, goes to right, it rotates to left, right. So remember that. So keep it in mind that. So best case is actually when, okay, let's consider the case when one photon goes left to right, left mirror to the right, then it rotates in the one way, and then here it gets flipped. But at the same time, axion oscillation changes its sign. Like axion started going to the opposite way, opposite direction. Then, so this circular polarization is flipped and axion direction is flipped. Then in that case, so photon linear polarization keep on going on the one way, same direction as the previous way. So in that case, we can achieve very good sensitivity. Do you understand?
Yes,
so
I do. And is that the resonant peak that we see?
Yes,
that we see at higher masses.
Yeah. Yes.
Yep.
That's why we have a very spiky feature and sensitivity curve. But
Okay.
in the low mass region for gravitational wave interferometer, so oscillation of mass axion, so oscillation frequency or like a period of axion is so long, so photon go back and forth within the cavity. So that time scale is much shorter. So almost all the rotation effects are canceled out. That's why it doesn't give you good sensitivity.
No, that's clear.
Yeah. But
so unless you're in the resonant region, a dedicated experiment is favorable as opposed to the parasitic measurement at LIGO.
So parasitic. So what does it mean?
Meaning it's not designed for it. You just, what you said, you add an extra detector and you don't change anything.
Yeah. And
yes. If you really believed that the mass was in that region, then it would be persuasive for LIGO to make the change, but not really otherwise.
Yep.
Thank you.
Yes. Thank you.
So can I ask you the question related with this gravitational observatories and the observations? In principle, you know, the axion or axion-like particle also couples to the gravity with a similar kind of coupling as to the photon. And in principle, we could expect birefringence effects, you know, polarization of gravitational wave by itself. And so that's something which LIGO wants to measure in principle. Have anyone estimated the effect, whether this is significant?
That's an interesting question. So you mean the phi allow-Childer coupling?
Yeah, the phi can be RR dual. Yes, exactly.
Yes, allow-dual.
I would assume the effect is very small, but you know, still, if anyone estimated, and
sorry, I don't know. I guess its effect is very small. But okay, let's go. Yeah, it's a Chern-Simon gravity. And so I'm not expert on that. So it's a modified gravity.
Yeah, I mean, it's the same thing. I mean, you have the same kind of birefringence effect for the gravitational waves. Yes.
I guess so. But sorry, I don't know. But that sounds very interesting. Possibility. If you can measure the rotation of gravitational wave.
Well, to my understanding, the measurement of the polarization of the gravitational waves is kind of next step for the advanced LIGO. So they will be doing that anyway.
Yeah.
And of course, in that sense, of course, LISA and the other experiments are maybe important as well. You don't rely on photon, right?
I see. Okay, then that sounds very exciting, like opportunity to search for Chern-Simon gravity.
Okay, thanks.
Yeah, so I don't know well, but that sounds interesting. And maybe somebody have already studied a bit. I don't know. Thank you for a good comment.
Can I just ask quickly about how you set the sensitivity for the ring cavity? What source of noise are you considering? Are you at the regime where you have to worry about vibrational noise, or is it just like Poisson noise?
Okay, yeah, we didn't consider any realistic noise. We just consider shot noise here. So yeah, okay, I'm not expert at all, but my collaborator says, so if you consider those kind of, let's say, seismic noise, so maybe on smaller scale. So you see, like here, our like a idealistic case. So for a lower mass region, so low frequency, so sensitivity curve looks very flat, and they can in principle it can go straight forever. But in reality, we guess that we need to confront we will confront some other noises, or even around here we may have some other noises rather than shot noise, but we don't know. So that's why we we are working on prototype to check what is noises, the sources of noise in a real experiment. So we hope to figure out what kind of noise are there and how to deal with them by using this prototype experiment. Yeah.
Okay. Do you have more questions?
One last question for me.
All right. I thought it was you. Go ahead.
Tomo, in one of the first plots that you showed, you had like a square that indicated the region in the mass coupling space that you could probe.
Okay.
I was just wondering what makes that square, like what kind of assumptions go into that? Is it just the nature of your experiment?
You mean this square?
Or yeah, is there like some theoretical assumption, or is it just the nature of the experiments that you are proposing?
Okay. So this square doesn't have any profound meaning, but maybe one thing is we have a lower bound for mass from the assumption that axion is dark matter. So in principle, just if you just say axion like particle, mass can be anything. Can be like infinitely small, but if you want your axion to be a dark matter, it cannot be smaller than 10⁻22 or 10⁻21. So that gives you this like a left edge.
Yeah. Okay. So should I introduce you as an experimentalist now?
Yeah, but I said experiment like it's empty region, but in reality there have already been a lot of proposals already with that. Yeah.
Yeah,
so
but yeah. Sorry, go ahead.
Yeah.
But what I mean is, when I met you, you were a theorist. Are you still a theorist?
I'm still a theorist, I believe, because I didn't go to lab and I don't handle cable or experiment. I just theoretically think about experiment.
Okay.
So
you're not planning to change.
No, once I asked my collaborator, so since I have already contributed to proposal, so I want to join the experiment. Yeah, I really want to, and I asked my colleague that how long does it take to be an experimentalist, to contribute experimentally to that sub proposal, this one. And he said you need at least 3 months of basic training to contribute.
Oh, that's not that
3 months. That's wrong. So that that comment a bit discouraged me, and so far I just stay remain a theorist. But who knows? Maybe in the near future, if I get bored or worked out all the theoretical possibility, then I will be an experimentalist.
Okay. Are there any other
Can I
questions?
just ask one really final quick thing? What's the difference between your experiment and ADBC? Because as far as I know,
Yes.
ADBC is like the same idea.
Yes, so ADBC, okay, that's my collaborator sometimes explained to me, and I never well understood. But ADBC is like a proposal after this dance experiment, and they improved the way that to achieve this sensitivity through this experiment, you need to be super careful to what's that? So this like a line of the photon, like a laser line should be on the same plane, but it's very difficult to keep it in the realistic experiment. So ADBC improved that difficulty. Anyways, I think the conclusion is ADBC is better than us in that sense. And another difference is ADBC is scanning one. ADBC adapt scanning strategy. So that means, so here is an ADBC sensitivity curve, and here is a dance one. But this ADBC sensitivity curves means ADBC sensitivity curve is not exactly the same as ours. So ADBC, like intrinsic sensitivity, has a spike feature, just like this advanced light case. So, and they change their angle of mirror such that like a spike sensitivity is scanning the parameter range of the axion. So they use a scan strategy, but we don't use that. I think
I was mainly just wondering whether or not the two groups were involved with each other, seeing as it seems like a very similar kind of experiment, but it seems like you're independent.
Yeah, no, like dance. Okay, so maybe my colleague can give you a much better answer, but he says, okay, this Michimura says he will adapt the ADBC technique in this prototype experiment. He will introduce the ADBC technique, not the scanning strategy, but the other one. Sorry, I don't remember well. So we are not completely separated. We know each other, and probably we borrow ideas each other.
Oh, thanks.